Hello everybody. In this video we're going to continue with Chapter 7 Statistics, and it's specifically 7.4, the last section of the chapter, Linear Regression. And we're going to start with the concepts of correlation and covariance. So first of all, let's talk about a scatter plot. Let's take a look at these three statements. The first one says, the total time you devote preparing for an exam affects the score you obtain in the exam. The next statement says, in general, the foot size of an adult is related to the height of that adult. And the last one is, smoking increases the chances of a heart attack. Statements such as these concern the relationship between two variables. So far, we have considered how to describe the characteristics of one variable. In this section, we will look at relationships between two variables. This area of mathematics is known as bivariate statistics. So in the next slide, you're going to find an example. And it says, here are the scores of 10 students in an IB chemistry standard level class. The table shows the time they spent preparing for the test and the scores they achieved. So here are the hours and the scores. And also notice that we have student names. Okay, so on the right-hand side, you're going to see a scatter plot, which is based on the data points given through the table. The horizontal axis shows the preparation time, and the vertical axis shows the scores achieved. So by looking at the graph, it appears that more hours spent preparing results in a higher score. So we say that the scores on tests and the time preparing for them are associated. Now, this is important. Time is what's called the explanatory variable or independent variable. And the grade is the response variable or dependent variable. The students whose time and scores are recorded are the subjects of the experiment or study. Okay, so next we're going to work on example 7.10. And it says, the data presented below is for 80 adults participating in a dieting program. The researchers believe that the metabolic rate, or calories burned per 24 hours, is influenced by the lean body mass in kilograms. So the question here is, does the scatter plot show that there is an association, remember that word we just saw, between the metabolic rate and lean mass? Well, I think it's easy to observe that there is definitely a positive association. Now, why do I say a positive association? Because the greater the lean mass, you can see that, the greater the lean mass, the higher the metabolic rate. The following example is 7.11. And it says the table below lists the fuel consumption in kilometers per liter of 34 small cars during both city driving and highway driving. Draw a scatter plot of the data and comment on any patterns you observe. So notice that they give us the raw data and we are going to build a scatter plot. To do that, we're going to use the GDC. So in order to build the scatter plot, we go to Stats and we edit the lists. And notice that I've already inputted in list 1 the data corresponding to the city consumption in kilometers per liters of 34 small cars. And in list 2, I have the consumption in highway. Okay, so next what you're going to do is that you're going to go to second and stat plot, and we're going to go to stat plot 1, make sure it's on, and then we're going to scroll down and we're going to choose the first type of graph, which is precisely the scatter plot. So in this case, the X list is going to be list 2, meaning that I want the highway on the X-axis. So the highway data will be on the X-axis, and therefore the city data will be on the y-axis. Then also notice that we can choose what kind of mark we want for the data points. I'm going to use little squares just because they're a bit smaller. And then remember that for these, we want to go to zoom and we want to choose number 9, which is zoom stat. So we hit enter and there it is. Okay, so now what can we comment about this? Notice that the data indicate that the fuel consumption in highway driving and also city driving are positively associated. Why positively? Well, because if we think of a line here, this has a positive slope, and the data points indicate that the relationship is strong because they are tightly clustered around a positively sloped line, as we can see here. However, you can see that there's one observation that is positioned quite far away from the rest of the data. So this is what is called, this here is an outlier. Now in statistics, outliers are important because sometimes they indicate that there's a problem in the data being observed, and sometimes they might have a special significance. In this case, what they say is that this little piece of data here corresponds to a hybrid car, which uses battery power in addition to fuel. So that's why it has such a high performance in relation to the other cars that are fueled normally. So because this observation is not typical of the study, we should remove it in order to get a clear indication of the nature of the relationship between the two variables. So next we're going to talk about covariance. And let's take a look at figure 10.17. Now the first thing you need to notice is that this line here is the x-axis, and this other line here is the y-axis. Then you also have two different lines that intersect each other at this point here. Now, what do these lines represent? Notice that this is mu x. So this is the average for all the values of x, and this is mu y, which is the average for the values of y. Now, in this case, everything is perfectly symmetrical because all of these data points fall in a straight line. So obviously, x and y are dependent in this case. So we're going to locate any point. Let's just say this point over here. And this point would have coordinates x1, comma y1. And then what we're going to do is that we're going to measure the deviations. So what are the deviations? Well, the deviations are the differences between x1 and the average for x, and y1 and the average for y. So what's going to happen here? Notice that in this case, x1 minus mu x is going to be positive because x1 is to the right of the average, and also this other deviation, y1 minus mu y, is also going to be positive. So the covariance is what's defined as, we write it as COV of xy is equal to the expectation, and this is going to be the multiplication of the deviations. So if we multiply this times this, so the deviation for x times the deviation for y, in this case that we just saw, this will be greater than 0 because they are both positive. So this tells us, what this indicates is that this data, or the pattern in this data, is going to be positively sloped because the product of deviations of the mean is positive. Now notice that we could also grab another data point below, and we would end up with a positive value as well. Well, because if we do the deviation for x, this would be negative. And if we do the deviation for y, this will also be negative, right? Then we would still have that the covariance would be positive. Therefore, it doesn't matter which data point you grab, it's always going to be positive. So that means, and as you can see in the graph, that there is a positive association. Now let's repeat the same process, but now using figure 10.18. So notice that this deviation here would be negative. Why? Because x is to the left of mu x. But this would be positive. Why? Because y1 is a larger value than the average for y, or mu y. So the covariance in this case would be negative. So that means that there is a negative association. So next we're going to take a look at correlation. Now, a scatter plot is a useful tool that reveals the form, trend, and strength of an association between two quantitative variables. In this course, we are only going to be interested in linear relationships. So as I said before, we say that a linear relationship is strong if the data are tightly packed around a line and weak if they are widely dispersed. But relying simply on the shape of the graph may be misleading. Take a look at these two scatter plots. Figure 10.20 is simply a copy of the graph in example 10.7. Now take a look at figure 10.21. It gives us an impression that the association is stronger than it is in figure 10.20. However, this is simply a trick. There has been a change in the scale on the vertical axis. So both scatter plots really represent the same situation. That means that we will need a different tool or a more robust measure to support our graphical impressions. And this measure is the correlation coefficient. So the correlation coefficient measures the strength and direction of the linear relationship between two quantitative variables. So for a set of data, xi, yi of size n, this is the formula for the correlation coefficient, where x bar and y bar are the means of the variables, and s sub x and s sub y are the standard deviations. Specific values of uppercase R are denoted by lowercase r. Okay, so notice that in reality, this is the covariance, and it's divided by the multiplication of the standard deviations. Now, it's important to notice also that R is also called the Pearson product moment correlation coefficient. In fact, R is an unbiased estimate of the population coefficient. So this is basically the same formula, but for the population. And in GDCs, you're going to find R. In exams, luckily, you won't be asked to calculate the coefficient by hand, but rather just to interpret the GDC result. So here we are again with those two graphs or two scatter plots where the scale for the city is changed on this one to the right, and it gives the impression of being a different scatter plot with these data points closely clustered together, as we can see here. However, if you run a function in the calculator, and these are two separate calculations, one for the graph to the left and the other one for the graph to the right, although they seem different because they have different scales for the city, it turns out that they have the same correlation coefficient R, as you can see here. So this is for the one on the left, and this is the one on the right, as you can see. So they give the same value. And notice that the correlation coefficient is close to 1, which means that they are very closely correlated. There is also another value, which is r squared. You see that? This r squared and r squared, which is also the same for both cases. Now, r squared is known as the coefficient of determination. And this is something that is not going to be required for the IB exam, but it's important to talk about it because it's interesting since it can be expressed as a percentage. So notice that it's about 88%. Yeah, in both cases, it's the same value, 88%. And what that implies is that 88% of the variation in city consumption can be explained by the variation in highway consumption. In other words, on average, for cars with the same characteristics, if there is a 1 kilometer per liter change in city consumption, then we can expect that 88% of this change can be explained by changes in the highway consumption. So next we're going to work on example 7.12. And it says, the table below gives us the data for a lab experiment involving the length in millimeters of a metal alloy bar used in electronic equipment when it is exposed to heat. So notice that we have temperature and the length of the metal alloy bar. So here, the explanatory variable or the independent variable is obviously the temperature because that is what is being manipulated in the experiment. Therefore, the length will be the response variable or the dependent variable. So we will put this on the x-axis and we will put this on the y-axis. So it says, draw a scatter plot. Comment on the strength of the relationship and then use both r and r squared. So we're going to go to the GDC to do this. So here we are with the GDC, and the first thing we're going to do is click on Stat and Edit. So notice that in list 1, I have the changes in temperature, and in list 2, I have the changes in the length of the bar. So now we're going to see the scatter plot. So let's go to Stat Plots and make sure that it is on. We choose the right type. And then we have to make sure that the X list is list 1, which represents the temperatures. And then the Y list would be list 2, which represents the lengths. So now let's go to Zoom and option number 9, which is Zoom Fit, right? And there we are. Just by looking at the scatter plot, there seems to be a relatively strong relationship. Notice that if we draw a line of best fit. Now, this is, of course, is not the exact line of best fit, but we can imagine one. And you can notice that the data points are relatively close to what would be the line of best fit. But we're going to confirm this by calculating the correlation coefficient. So to do that, we need to go to Stats. So let's click on Stats and then Calculate. And you're going to scroll down to where it says linear regression, but not number 4 because this is not the linear regression for stats. We want to go down to number 8 and notice that it says linear regression A plus BX. So A would be the y-intercept and B would be the rate of change. But this is for statistics. So let's hit on enter and it says linear regression A plus BX. Let's click on enter there. And notice that we get the data that we're looking for. So if you look at R, which is the correlation coefficient, it tells us that it is about 0.955, as you can see here, right? 0.955. So that means that there's a pretty strong correlation. Now, if we look at R squared over here, which is about 91.2% for R squared. What this implies is that 91.2% of the variation in the length of the bar can be explained by the variation in the temperature. So now we're going to take a look at some properties of the correlation coefficient. So the correlation coefficient is a measure of the strength of the linear association between two quantitative variables. Do not apply correlation to non-quantitative data. Well, this is obvious, right? It won't work with qualitative data. The coefficient does not prove a linear relationship, but if there is a linear relationship or association, the coefficient will describe its strength. Outliers can distort the correlation coefficient, so special attention must be paid to outliers. We saw that before. The correlation coefficient is always a number between -1 and +1. Values of R near 0 indicate weak or no relationship. Values that are close to +1 or -1 indicate a strong association. R is independent of the units of measurements or the scale as we saw previously. R has no units and it is not a percentage. For example, do not express correlation of 0.85 as 85%. This would be wrong. Then finally, correlation between two variables means that there's some association between them, but it does not mean that one of them causes the other. And this is a very important point because correlation does not mean causation. What would be a good example? Well, for instance, let's suppose we go to a beach and we measure the consumption of ice cream, but we also compare that to shark attacks. Now, we might have a correlation that implies a certain association between consumption of ice cream and shark attacks. So the more ice cream is consumed, the more shark attacks there are. Now this could be a correlation, but not a causation. It doesn't mean that if people eat ice cream, they will be attacked by sharks. What it means is that there's more people on the beach in summer, and there's more consumption of ice cream, and more people are exposed as well to shark attacks. So now we're going to take a look at what is called the least squares regression. And first, let's talk about a regression line. So in the previous example, you saw that I sort of drew a regression line. Now that was just an estimate, right? There are mathematical methods to actually find a regression line. So a regression line is a straight line that describes how a response variable changes with changes in the explanatory variable. So basically what they're saying is that we can come up with a linear function that can represent a regression line, or also known as the line of best fit. And it's symbolized with this. So this means expectation for y is equal to alpha plus beta times x. Now in the calculator, you will see it as y is equal to a plus b times x. Now this is simply a linear function, where this would be the y-intercept, and this would be the slope, or the rate of change for x. So why the least squares regression line? Let's take a look at this example. The first thing to notice here is that the line of regression goes through the point x bar, y bar, which is the average for x and the average for y. So this graph represents a few points in a data set. As you can see, these would be the points in the data set. And the green line is the line of best fit. So let's take, for example, the point x1, y1. So this is part of the data set, x1, y1. And the point x1, y hat 1, which represents the prediction from the line of best fit. So the distance y1 minus y hat 1 is the error in the prediction from the line of best fit. So this would be an error right here, this difference. Similarly, this difference here would be an error, where you see that you have y2 minus y hat 2. This would also be an error, this difference there, and this difference here. So the line of best fit is a line that minimizes the sum of all these errors. However, like the variance, some of these errors are positive. So this is a positive error and this is a positive error. But other errors are negative. This is a negative error and this is a negative error. So if we sum them, they would cancel each other out. So to avoid this, we do what we did with the variance. What we do is we minimize the squares of these errors. So that means that the line of best fit is the line that minimizes the sum using sigma notation. So it would be y sub I minus y hat sub I squared. So that's why it's called the least squares line of regression, and it's symbolized with y hat is equal to bx plus a. The next example is 7.13, and it says, this scatter plot represents a random sample of IB students who went through 4 years of university and is a comparison of their scores on the IB exams they took and their GPAs in their university studies, scale 1 to 4. So, in this case, the explanatory variable or independent variable is obviously the IB score, and the response variable or dependent variable will be the GPA. Now, they tell us that when they found the linear regression for this set of data, it is that the GPA is equal to minus 1.51 plus 0.151 times the IB grade. So this means that on average, for every point that the IB grade goes up, you would have an increase of about 0.15 points in the GPA. Now, if we wanted to predict, for instance, the GPA of a student who scored 30 on an IB diploma, then we could say that we could predict the GPA. Say the GPA should equal about minus 1.51 plus 0.151 times 30. And this is going to equal 3.02. So somebody that scored 30 points on the IB diploma would get a GPA of 3.02. Now, the correlation coefficient that they give us in this example says that R is equal to 0.758. So this is relatively strong because it's kind of close to 1. They also give us the R squared, and in this case, it's 57.5%. So what it means is that the changes in the IB score may help us explain 57.5% of the variation in the GPA. Now, this does not mean that high IB scores will cause high university grades, but it helps predict the future university grades. We continue with example 7.14. And it says, here are data for two variables, x and y. Draw the line of regression and indicate the distances, the sum of whose squares is minimized by the choice of the line of regression. Okay, so for this, we're going to use the GDC. So again, we go to Stats and Edit, and then in L1 or List 1, I put in all the x values, and in List 2, I put in the y values. So now let's go to Zoom and option 9, and there it is. So now let's take a look at the line of regression. So for that, we want to go to Stats again, and then Calculate. And remember that we go to option number 8, which is linreg, or line of regression, in the form a plus bx. So let's hit enter, and it says line of regression. And for this, we have to make sure we use L1, so 1, comma, L2, just to be sure. And then we hit enter, and there it is. Notice that we have y equals a plus bx. The a value should be 6.14, and b would be 2.071. So we're going to graph y is equal to 6.14 plus 2.071x, right? So let's go to y equals and plug that in. So we would say 6.14 plus 2.071 x. And then let's hit graph. And there is the regression line. Now, let's use a trace, and notice that the scatter plot represents the points from the table. So 11.21, and then 12.43, 13.31, and so forth. So next, what we're going to do is that we're going to find all the distances. So the distance between this point from the scatter plot and the line, as well as all the other ones, right? All of these distances. So let's go back to the presentation. So the line that we graphed was y hat is equal to 6.14 plus 2.071x, right? Here are the x values, and here are the y values, the actual data. Now the fit, where does this number come from? It comes from plugging in 11 into the line of regression. So the fit represents all the values we would get when we plug in the x value. So notice that here we have 31 and so forth, right? Okay, then the distance is going to be the difference between them. So notice that 21 minus 28.92857 is going to be negative 7.9857, and then so forth, right? These will be all the differences which represent the distance. Then we would square these distances to get positive values. We would add them all up, and the minimum sum is going to be 596.71. Now you could try to find any other line, and you're going to notice that this line here is the minimum sum of the squares of distances. So there's no other line that is going to have a lower sum of the squares of distances. Also, the mean for x bar is equal to 14, and then we also have that y bar, or the mean for y, is 35.14. So what happens when you plug in 14 into the formula? Notice here that when you plug in 14, you get 35.14, which is the average. That means that the line contains the point x bar comma y bar, which is a requirement for lines of regression. So now we continue with example 7.15, and it says the following data represents the volume in cubic centimeters and the weight in grams of a certain fruit studied by a biologist. So X represents volume of the fruit and Y represents the weight. So it says obtain the least squares regression line of Y on X as well as the regression of X on Y. Use the model to predict the weight of 230 cubic centimeter fruit and also predict the volume of a 168 gram fruit. So for this, we're going to use the GDC. So as usual, we want to go to Stats and Edit, and notice that I have already entered in list 1 the volumes, and in list 2, the weights. So we want to find the regression line, right? Or the least squares regression line. So let's just go to stats again, and we go to calculate, and remember that it's option number 8, and it's linear regression, a plus bx. Now, it says that first they want us to find it of y on x. So that means that x is the independent variable and y is the dependent variable. Remember that is also called the explanatory variable when it's x, or the independent variable, and the response variable, normally y, which is the dependent variable. So here we're going to do for x list 1. So let's make sure we go second and 1, and then comma list 2. So second and 2. And then after that we can hit enter, and there it is. So notice that we get the regression line equation. Y would be equal to approximately 115 plus 0.233 times x. So we have our first regression line. Now let's do the opposite one, right? So for that, let's go back to stats and calculate, option 8, and the same thing again, but this time we're going to do it backwards because we want y to be the explanatory variable, or the independent, and then x is going to be the response. So let's say then L2, comma L1. And let's hit enter. And there we go. Now we have a different equation. Notice that now A is 56.1 and B is 1.02 approximately. So we have our two equations. So let's solve the questions that they had, right? So let's go back to the whiteboard here and let's write the equations that we found. So we found first y is equal to 115 plus 0.233 times x. Okay, so y was the weight, so we can say the weight is equal to 115 plus 0.233 times the volume. And then the other one we found was x is equal to 56.1 plus 1.02 times y, right? Or, in other words, the volume is equal to 56.1 plus 1.02 times the weight. So let's focus on these two equations because these are the ones that are going to solve the problem for us, right? Because they wanted to find, they said, use the model to predict the weight. So for this one, we'll use this, the weight of a 230 cubic centimeter fruit. And then they say, predict the volume, so we'd use this one for that, of a 168 gram fruit. So all we have to do is plug this in, right? So W, the weight, is going to equal 115 plus 0.233 times 230. And then from this, we're going to get that the weight is 168.22 grams. So that's the weight of a 230 cubic centimeter fruit. And then let's find the volume of a fruit that weighs 168 grams. So this is going to be, the volume is equal to 56.1 plus 1.02 times 168. Plug that into the calculator, and you are going to get about 227.26 cubic centimeters.